So first, before we get started, if you want to follow along on your phone, that's better. Okay. If you want to follow along, you can just go to sethsamuel.github.io. The first link there will be to this talk. I am Seth. I'm here to talk about WebGL for more than graphics. I'm from New York City. I've been in New York, Portland, various other places, Portland, New York. I can never move again because it would destroy the symmetry of where I've lived, and I'm much too compulsive for that. I'm Seth F. Samuel on Twitter and Seth Samuel on GitHub, where you can find all these slides and all the code for the demos. All right. Before we get started, quick disclaimer. This is a talk that goes really deep in the weeds. It's pretty weird. I think it's fun, and hopefully everyone will get something out of it. I also talk really fast and use a lot of idioms like deep in the weeds, so I apologize to the translator in advance, and if any of you get lost, it's totally my fault, not yours. Come find me afterwards, ask me questions. I love talking about this stuff. All right, what's WebGL? So if you haven't worked with WebGL before, WebGL is a JavaScript API that lets browser developers write code that runs on the graphics card. So normally when you're writing JavaScript, it lives inside the browser sandbox. And what WebGL does is take your JavaScript code that looks a lot like OpenGL code, if you've ever worked with OpenGL, bundles it up, ships it off to the operating system hands it off to the graphics card, and eventually it paints pixels back onto the canvas. So it basically draws an image. And that canvas we can access with JavaScript like any other HTML canvas. So this is the basic pipeline of a WebGL application. You put in data. That data goes through a vertex shader. The vertex shader takes the data and turns it into points in three-dimensional space. So the most straightforward thing is pass in data that looks like points in three-dimensional space, like XYZ coordinates. You might do something fancier like put in audio so that you can have a visualizer of the sound. The vertex shader passes those 3D coordinates to the fragment shader, which draws the colors that will eventually show up back on your canvas. So the fragment here is if you imagine a triangle, that fragment of space, that's what it's coloring with the fragment shader. And then it just writes graphics. And what's cool about this is it does this all in parallel. So if you have lots and lots of graphics, it calculates all those vertices and it calculates those colors all at the same time, rather than having to iterate through every single pixel. All right, so simple gradient, and hopefully, yeah, that's mostly visible. Because GLSL, which is the language we write shaders in, is heavily based on C, it uses lovely concepts like to return a value, you set a global variable called glFragColor. And you set it to a vec4, which is just a really fancy name for an RGBA tuple. So what we're going to do here is we're going to take S and T, which are where we are in the square, Y, S, and T, and not X and Y, because the square, in our example, is just going to be sitting right in front of us. But if we're in a 3D application, it might be rotated all through space, and you don't want to confuse the X, Y of space with the ST of where you're sitting on your square. And we're just going to set the red to S, the green to T, blue's going to be 0, and alpha's going to be 1. And that's what we get. So this is actual WebGL code running embedded inside of these slides. And you can see in the top left corner where we're at 0, 0, everything's black. Then we got red, green, yellow, where both of those are 1. Cool. Edge finder. So an edge finder is if you have an image and you want to find the points that our sort of brains intuitively see as edges, what you do is you step through it, you look at every pixel, you look a little bit to the side, and if they're very different, that's an edge. And so here, we're going to look at the pixel to the left of ourselves. So this is running at every single pixel within the image. And we're going to look at ourselves, we're going to look at the pixel a little bit to the left. If the distance between us as colors is beyond a certain threshold, then we're going to set the color to be purple, otherwise we're just going to set it to be black. So a small child attempting to eat an entire block of cheese, because cheese is delicious. And there we have the edges inside that image. And you can see, there we go. As we change the threshold, so how big a distance in color we're looking for, if we go all the way up here and we set it really low, so any tiny difference in color is an edge, then the whole thing looks like edges. And if we set it all the way down here, so we need the colors to be really different, then every single, or very few pixels are edges. And you can see, if I can click, there we go. I'm doing this, and it's updating in real time. It's going 60 frames a second, and this is a 1024 by 1024 image, so it's 1 million pixels that it's running that calculation on. and it's doing it perfectly smoothly. You can write an edge defender like this in JavaScript, but you won't be able to do that on an image of this size because it's just going to not be able to keep up. All right, particles. It's not a WebGL talk without a particles demo. So here we're going to be working in the vertex shader. So instead of setting colors, we're going to be setting position. And what we're going to do is we're going to set the x to be math and then sine, the y to be math and then cosine. You might point out sine and cosine are also math, but the point is that they're swirly math, and want to make clear that's where the swirliness in this demo comes from. All right, and that's totally not visible on the screen, so we're going to add more. There we go, more pixels. All right, so that's 100,000, 200,000, 300. Yeah, it's starting to get a little laggy now. So on my little MacBook Pro, which is not exactly a graphics powerhouse, there's 300,000 pixels flying through space. And again, super fast because it's calculating each of those pixels at the same time. All right, so why? You might have caught on. Because it's all at the same time. So you have two main processors inside of your computer. You have a CPU and a GPU. A CPU is a general purpose processor. It's good at doing lots of things pretty well. And by pretty well, we mean here I have all of humankind knowledge in my pocket right now. But it's not as good as the GPU at doing really specific things. So the GPU is really good at doing small math operations all at once. So suppose you wanted to do thousands of kindergartners' math homework at the same time. I don't know if kindergarten is the same here. 6-year-old math homework at the same time. That's what a GPU is really good for. Really simple math all at once. So someone came up with the idea, wait a second, this works great for graphics, but it would also be great for a lot of calculations we want to do. There's lots of scientific applications, there's lots of computing applications where we could do really great things with this graphics power without actually drawing graphics. And this sort of, why do we have to make it look like graphics? We shouldn't. So WebGL is based on OpenGL, and the complement to OpenGL is OpenCL, which is the Open Computing Library, which makes it much easier to do all of these math operations without having to pretend we're doing graphics. So if WebGL lets us do OpenGL in the browser, what lets us do OpenCL in the browser? There's WebCL. It's coming soon. It's not coming soon. We're never getting WebCL. There's compute shaders, which are a lot like fragment and vertex shaders. They're also coming soon. They're probably never showing up in the browser. I think they were sort of starting to work on these, but they're also probably dying. So basically, the two ways that we would really want to do this cleanly are sort of held up in committee, and at the same time they've been working on these. OpenGL has mainly been supplanted by other graphics libraries. So we're going to be waiting a while before we can do all this stuff the right way. But we're programmers. We like doing things the wrong way. We're at a JavaScript conference. Risky joke. So if we can get the data in and we can do the math, how do we get the data out? And the answer is pixels. And why is the answer pixels? Because we don't have anything else. That whole browser sandbox blocks us from getting anything directly from OpenGL. All we have is the pixels that come back. So that's OK, because pixels are just data. Every pixel is just an RGBA tuple, which is 8 bits, 8 bits. It's 32 bits of data. So on every single pixel on a WebGL canvas, we have 32 bits of data that we can just extract. It looks like a color, but we can just treat it like numbers. Is that me? Oh, I don't know what I'm doing, but I'm sorry. And we can get it out because it's an HTML canvas, and we have get image data, which just returns every pixel in the canvas as an array of data. All right. Implementation challenges, it's not that simple. The main one here is that serialization is really expensive. It's expensive to get data into OpenGL, and it's really expensive to get it out of the canvas. It's roughly linear with the number of pixels in the canvas, and if you want to do large data sets, that's a lot of pixels. So we're not going to be able to do applications where we want to just send little bits of data off to the graphics card and get them back. So we want to take big bits of data, send them to the graphics card, and then get stuff back. And it turns out matrix multiplication is a great application for this. So your graphics card is already doing lots of small matrix multiplication, but we're going to do big matrix multiplication. Quick refresher for those of you who have not done matrix multiplication since linear algebra, or like me, kind of napped through linear algebra, or never took it at all. It's cool. We're going to have a quick review. So we all know multiplication, numbers times numbers. Matrices are just tables of numbers. and we want to define multiplication on these tables of numbers. And so the way we do that is we take the rows in the left matrix and the columns in the right. We multiply the numbers inside them and add them together. So 0 times 8 plus 2 times 6 is 12. And then this one we move over 1. 0 times 1 is 0 plus 2 times 7. This one's an easy one. I like when there's a 0 in this demo because it makes the math a lot easier. This one doesn't have a 0, so 3 times 1 plus 5 times 7 is 38, and you can sort of see how that extends to bigger and bigger matrices. All right, so it turns out we can do that iteration across the rows and columns in WebGL. If we just think of our output canvas as that final product matrix, for every single pixel, we're going to take the left matrix and then iterate through a row, and the right matrix and iterate through a column, add them together, and then put the sum into the color. All right, so here we got a 3x3 matrix, and we're going to do some math. All right, cool. So 3x3 matrix on the CPU is pretty fast. So the CPU here, we just have a JavaScript implementation that steps through each element, does all the math, and so it's pretty fast for 3x3. In fact, the GPU is slower because of that cost of getting the data in and out. So let's bump this up to 64 by 64. All right, I'm still only showing 3x3 here because my screen's not that big, but trust me, there's 64 by 64 on each of these matrices. So CPU took a little longer. And already the GPU is faster. So this is still pretty small matrices, and the GPU is about twice as fast. The numbers are the same, which is what you want to see, because if they were different, it probably wouldn't do us much good. All right, let's go up to 1024. So this is 1,000 elements across and 1,000 elements down, so that's 1,000,000 elements in each matrix that we're going to multiply together. And let's do it on the CPU. This is going to take a little while. This is the part of my talk where I just get to talk whatever I want about. So just to let you, oops. So we're using, probably can't quite, the zoom button does not work in Activity Monitor. We're using 100% of the CPU right now. We also can't get, there it is. Cool. Oh, good, it's still working. So we are using 100% of the computer's CPU right now. This window's totally unresponsive. If I tried to click on another button or move that slider, it would not work. The spinner's still spinning, which is pretty cool when you think about the fact that the browser's totally unresponsive. And the reason is that spinner is working on the graphics card. So if you know about, and yeah, that's going to happen. That's lesson number 2 during this break. We don't have to touch that because when you get that warning, it doesn't actually pause JavaScript execution. So if you hit a really nasty site where it's just killing you with JavaScript, it's still running in the background while you take the time to decide whether to kill it or not. I'm going to, well, wait this time. I might get distracted and not hit it, but it's okay because it's still running. So the spinner is spinning because it's just a div with a fill and a width and a height and an absolute position and a CSS transform on it. So CSS transforms are GPU accelerated, which is great. It means that the work you're doing for your animations aren't taking up CPU. But, there's a but. To actually start that spinning, I'm using a pretty normal method, which is I add a class to it, like active or something like that. And to add that class onto the element and trigger a DOM refresh and trigger a relayout, which eventually the browser realizes, oh, that thing should be spinning on the GPU, takes CPU time. So when I hit Go CPU, it actually waits a couple hundred milliseconds before it actually starts the calculation because it needs to give the DOM time to recognize that this class has been added, start the thing spinning, and ship it off to the GPU so that it can keep working while this window is completely unresponsive. This also leads into a nice little UX tip, which is this is not a terrible thing. If you probably didn't notice in the earlier bits, but in the small matrix size, it actually spun for about half a second, even though the CPU and GPU times were in the milliseconds. And that's because it's not a horrible thing to show a spinner long enough for your user to recognize there's actually a spinner there and not just a flash of something they don't know. This is going to finish eventually. One last thing. I'm cheating here a little bit. I made a mistake in the JavaScript implementation. It's not a mistake. It's doing the right math. So in that top right corner, there's a text box, or I just spoil it. There's an input, if you get the value of an input, what's the type of the value you get back? It's a string. If you do a for loop and use that string as your I less than whatever and your j less than whatever, the browser has to force that to look like a number. So here, when we're doing a billion with a Carl Sagan B operations, every single step in that loop, it's trying to force that string to be a number so that it can do the loop comparison. And it turns out that over a billion operations, that adds up. This is still really slow, even without that cheating, but I left it in because it's more impressive when it's super, super slow. This is still going. Wow. So this on my, last time I did this demo, I did on my MacBook Air. And this computer is it's faster than an Air, though it's really aggressive about showing me that warning. It still takes a really long time here. It actually took longer when I ran it on the Air. I tried running it on my gaming machine at home. I have a desktop machine for gaming. It's pretty beefy, and it's still really long. So that's a big number. Yeah. So we're into the region of benchmarking where milliseconds is probably not the right unit here. That's 237,000 milliseconds. It's about 3.5 minutes. Yeah, it's a long time. And yeah, milliseconds, it's really important that we know that it took 0.38 milliseconds at the end there. That precision is really what makes it. All right, so I should probably think of something to talk about during the GPU section. Nope, I don't need to. So that's faster. 1,000, that's 500 times faster. Yeah, that's whoa faster. So why? All right, quick refresher on big O notation. Basically, what we're looking at here, if n is the width of the matrix, then on the GPU, we're doing n operations because we're calculating every single one of the output pixels at the same time, and each one has to go through a row and a column. So that's about n. In the CPU, we have to go to n times n, because that's the number in the product, times n, because each product piece has to do a full loop. So it turns out n is less than n cubed for most n. And to show you sort of a little more, and I have n squared on here, that edge finder, that's n squared because you have to step through every pixel, which is n times n. So that's mostly visible. So the big one, that's n cubed, the one in the middle is n squared, and the bottom one's n. This is from 0 to 5. So we went to 1024 before. Here's 0 to 10, n's already kind of disappearing. 0 to 100, and now we can't really tell the difference between n and n squared. And it doesn't actually draw the n and the n squared because n cubed has gotten so big. So that's the savings we're getting by doing these operations in parallel. All right, cool. So we got a proof of concept. It's way faster. What could we use this for in practice? Because I know when I write talks, it's all about how can I use this code in production. Like no code review, just like ship it to production. It's fine. All right, hash collision. You're looking for when hashes collide. If you're a black hat hacker, it's because you're trying to crack a database. If you're a white hat hacker, it's because it's because you're trying to make sure people can't crack your databases. Bitcoin mining, all Bitcoin mining is done on the GPU. Just flat out, if you're mining Bitcoins or any other sort of blockchain type thing, it's done on the GPU. Media encoding, all parallel, all block-based. Machine learning is a lot of math, but lots of little math. Signal analysis and processing, I feel a little guilty. This is kind of cheating because sound and images are really all just signals, but we conceptualize them differently, so it's possible. Protein folding. Some of these are probably sounding familiar if you ever had one of those screensavers that does work distributedly, because it's the same problem. How can you take a lot of data, split it up, put it on people's graphics cards, and collect the result? All right, actual applications. Nope. 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 Maybe. Maybe. All right, so why is it that we can't do all that good stuff at the beginning? This is the main one. So the version of GLSL, which is the shader programming language in WebGL, is super old. They built WebGL about 4 or 5 years ago now. They took the current GLSL version and they've never bothered to update it since. They added bit operations in a more recent version of GLSL, but the browsers haven't been updated. And Unfortunately, very smart people have spent the last 50 years or so figuring out how to do really good stuff with bits. Because it turns out our computers think in bits, and if you can make your algorithms based on bit operations, they run really well on computers. But we can't actually do them, and that slows us down a ton. It's why we can't do any of the hashing or the encoding or any of that. Unresponsive window, you probably didn't pick up on it there, but if you watch it enough times, you can see the spinner lags on the GPU version for about half a second, because it turns out the GPU can only do one thing-ish at a time, and your operating system does a decent job of sort of separating different different programs and how they're taking up GPU time, but your browser window only gets one GPU segment. So if you are doing a bunch of math on GPU, you're not going to be able to interact with anything on the page, and we're back to the bad old days of CPU calculations blocking things. And this is a fun gotcha. It's not really a practical limit in most cases, but different operating systems have different timeouts for shaders. They have sort of baked-in safety mechanisms that say you're not allowed to just send a program off to the GPU and just take up the GPU forever. And they're not really well documented. They don't really give you a good return value. Sometimes it's black, sometimes it's transparent, sometimes it's whatever touched the color last. So if you have really long-running shaders, this can really be a pain in the ass. All right, so what if we wanted to make this actually work? Newer shader library. This is relatively straightforward, but just like the WebGL and the compute shaders coming soon, it's something that kind of lacks impetus behind it because a lot of people are thinking that OpenGL and WebGL are just sort of going the way of the dinosaur anyway. But if the browsers decided to update to newer GLSL tomorrow, we could do all that cool Bitcoin stuff. Canvas, WebGL, and WebWorker. This is sort of done in Firefox. It's coming in the other browsers. It's going to be great for lots of things, but it would also be great for this because then you wouldn't worry about locking up your window with all this computation. So, sum up. WebGL is awesome. It's really fun for doing graphic stuff, and you can, with a little bit of coaxing, make it do even crazier things, which are also a lot of fun. And that's it. Thank you.